Okay guys, so same structure. This is from, now we're on the video 5. I'm going to post a 3A, so it's a 3 and then a 3A. But in this, from the video number 5, I cut, let me make sure I have the right video view, different camera. Gotta go this side. Don't want to block your lighting. So I cut number 11. See, it's cut. The bar has been detensioned, totally detensioned. The nut is off. That's important. That will stop, if the nut's on, the range will be limited by when it hits the ends of the nuts, when it hits the limits. We'll keep it on just a hair. I'm going to put an insignificant, not really insignificant, but just a touch of load on the center there. I'm going to zoom back in there and I want you to watch with this little bit of a load. Let's see if I can get it. Let's see if I can have it. This time I will not be able to stand on it. With this, it's just going to be a little hand pressure. And you're going to watch the deflection. A little bit of hand pressure. And all I did was put a little bit of pressure, downward force right here. A little bit this time. A little bit, like, doesn't take much at all. So this deflection is what creates this reaction down here. This reaction down here isn't created on its own. It has to have a load on it. Right now, this is the dead load of this scaled model, not scaled to weight, scaled to size, plus or minus 3/8 of an inch max, I would say. This deflection here in the deck, and the canopy and deck, will create the reaction out there. Now but that's a compressive crack. Initially, I think when it initially had a downward force, the deflection, because we have the deflection happening at the moment they detension. That's in video number 3A, I think it is. And now you see right here under attachments, cracks report after shoring removal. So they had the cracks there. So it's a lie to state that there are no cracks presented. This is part of the report. You guys can look at it, that they're talking about nodal area, etc. This is where all this drama seems to be focused on. Yet it's not the nodal area, it's secondary is the nodal area. The primary is sagging of the deck. That's primary. Secondary, this is very important, that little notch blue thing. We'll get to that. Look where it says round about the third, fourth one up. It says FIU commented to figure that nothing predicted this cracking. Clamping action on transverse strands. Now, Erica is the one that's supposed to be doing this post-tensioning, I think. There's something else about this. They're going to add the shims after to part of their product to help fix this issue. But yet, the shims are what also going to contribute to the failure, because they're going to create a new moment, a new connection, a new pinned connection, if you will, based on the weight. And that's going to make that new hinge point for your engineers out there. The shims created a new pin point. When they created the new clamping force, they had the 2 pin points and just broke it in the middle. And, of course, now we have these cracks. These are not compressive. They are, because what I just showed you, how that torque action took place. This is terrible. This is terrible to keep this hidden from the public also. I think I have it in 3A. That's what's important, and I've talked about this before, that they talk about the cracks happen when they took the forms away. Just a little bit of deflection. It doesn't happen on its own. This does not elongate and start pushing on its own. It needs a force to make it react down there. When we post-tension this back, when you put the post-tensioning back on it, in the rod, this helps hold that connection together. And so let me do that real quickly. I'm just going to do it live for you. Post-tensioning it back up. So now, of course, it's limited to the bar now when I put the deflection on it. it appears to be a smaller, it is a smaller range. Let me make sure where I'm filming. Yeah. So it is a smaller range that it will cause destruction, if you will. Once you detension, though, that range is now gets all the way out to, well, whatever it's detention to. And as they detension, it says it cracked like hell. It didn't really crack like hell. It was already there, as we show in 3A, video 3A, and other videos. Show the small hairline crack on the deck. That was the exact path of the current failure. So this already failed inside the staging area, and that's because of deflection. George, stop it. That's because of deflection. Let's pull the rod out. It's stuck now. The rod's got threads on it. So now you can see the rod's out, and now we can get a super bypass. This has the sagging is so much that it lifts up, but the loads now are taking place between 910 and the deck. This is no longer participating. 12 has already shown it's not participating, however you look at it, the very beginning or not. The bars are what are holding this together. What's participating is helping holding this together is the bar in number 11 is still there. And so is the one in 12. They've just been detensioned. So as the structure rebites, cracks like hell on the 10th, when they take the tension off 11, it repositions. All it did was the loads here deflected. This had a pulling down effect right here, downwards. Not so much as I'm showing here, because we don't have a compressive or bypass. See the bypass here? It's bypassing. It's not bypassing. It's actually pulling away, opening up. So that means there's more deflection right here and here than I can present with my model being steel. That I would have to load it to show you. Let's see if we can do that again. That bypass doesn't exist though, because the cracks are of an open nature, not of that nature. The forces are being resolved in the post-tensioning in the deck and in the canopy. And this will be a top flange, wide bottom flange, and down to here. So they come to 9, work their way out. Also from 9 to here, but the span between here is supported structurally by number 10 and 9. So it's able to say, you know what, I can transfer that load back down 10, take it up into this node here, and we'll still try to make the forces out to the end by coming across the top, 9 and 10. But at some point this is not structural anymore, it just breaks away. And all the loads on the deck at that point, when it cracks like hell, when it cracks like hell, remember it's already been detension in the staging area, these cracks have already presented themselves. It's already waiting for the detensioning to happen to cause it to expose, to develop it more, develop the cracks so you can see them further. Then they're called the cracks like hell, which nobody can evaluate yet. And per the presentation, you see it here. It's unclear how the change in distribution did it. They aren't clear about the being supported on shims could possibly lead to these top spalls. Question mark. He's not even sure if they're spalls. He put question mark on there. They're not spalls. They're indicating of the, well, they may be a spall, but they're indicating of the tensile forces that created because of this thing in the torque action already. Let me get back to the video. Yet they had photographs of the hairline crack in the same path as previously. The person that took the photograph should have realized the significance of that crack being the same as the crack there. Should have said, wait a minute, this crack is the same. Only thing we did different was we got rid of the clamp force. And that clamp force was what was helping this. Now there's another caveat, another toss in here that's going to really help this bridge get to failure. But right now it cracks like hell. It rebites onto number 11 is still in there, 11A bar, and 12 B bar, the upper bar. So I'm just going to just snug it up to there without doing too much. I don't want it to lock in really. It's kind of a pain to get it out, believe it or not. It's not that easy. So now it can only deflect as much as this will allow it, because this is a cable, you know, a bar. It's holding it back from deflecting outwards, from going outwards. That's when it rebites. That's the day of the 10th through the 15th, the fourth failure. It's like that. See the deflection there? So we get the deflection, but this is also up because this deflects up right here because we have some reinforcement in there that's also resisting. Now, put shims under this now. So let's take this away. Let's pretend like it's now on the base. It's the pure cap. There's shims under 12 now. When they go to post tension this is going to drag. That shim now has contact with the pure cap, with the pure top, right? Top of the pure. And it's going to drag. That's going to create resistance. But it's already cracked. It's already got a cold joint in here, which the NTSB or OSHA report, whichever one, states, oh, I think it's a, one of them say it's a monolithic pour. This is not a monolithic pour. The deck is poured first, including a blister out here. This part here would be a secondary, a primary pour with this one. Secondary pour would be up here, including number 11. So these two are poured together with a slight bit of chamfer in the middle. So now you have this cold joint with some steel there, and you want to, the Denny Pate tells them to put it back together. Well, you can imagine it's got a drag. Number 11's fair game. It can get 11 because 11's in the deck. It can create that compressive moment inside here. It's tied to the inside terminal of the diaphragm. It can compress, and we can see in the photographs from the NTSB OSHA report, the photographs show that, well, their number 11 didn't blow out. It didn't blast through. The back of the 8-inch plate didn't come through the concrete. There's no blowout there. But we clearly have blowout in number 12, the base of this. Well, imagine if this is a cold joint and you now are applying forces right about thereupon at the cold joint, and your friction is here on the shims now. So it's not elevated and then you brought it in and then fix the joint and then put it back down the shims. No, they put it on the shims. So look what happens as you try to push. It's got a cantilever. See the action? It's going to try to straighten itself back up. It can't do that, of course. It can't do that. It doesn't have the ability to lift up 925 tons. You know, I can count 25 tons before it's back. I don't know what I'm counting back here, actually. So let's just discount that. But it doesn't have the ability to ratchet back up, level the deck, back up to the fine hair crack. As Denny Page said, put it back to where it was on Saturday. Put it back before. Right, so you can't put it back, especially now because I mentioned it and we identify that it's separated now. So when you're separated by even that little bit of a ½ inch to 1 inch plus, and you go to crank this plate inwards, you're creating a moment right here. Right, this is that rod. Look at my hand, bow in. It doesn't have the ability to just stay flat and drag in. So this is what I'm going to refer to as the kinetic energy built up inside that clamp force was not resolved. And when they were post-tensioning the lower number 11, well, it resolved itself. I think it along with the deck's kinetic energy, it's a constant moving energy. It's not in equilibrium yet, so that's why I refer to it as kinetic energy. That it's not found equilibrium, it's not found its match, it's equal resistance. So therefore, it's still working in a accelerated, which is going to irritate some people, an accelerated creep process, and that's going down towards the ground. But the kinetic energy is there, and it's not met at equal resistance. So therefore, it's present, it's active, and it's working on there. Think of it as someone leaning against you. Initially, you can hold them back while they're leaning against you, but they're not going to increase their weight. But eventually, you're not going to be able to keep holding them back, and then you're going to fall over if they don't stop. You know, if they keep that force going towards you. It's the same thing here. Terminating that part of my explanation. So I'm going to have more videos. I muted this part to explain the drag that's taking place and the reaction that you created a pin point, a pin connection when they shimmed it. So when the repair created a new pin connection, it was floating in the air before, but that new pin connection and then you applying the force in the center of this mass, if you will, and then putting 300,000 pounds of force on it is not the same because it's no longer where it was. It's a ½ inch or a 1 inch gap. We don't know exactly where it was. They did no x-ray on the damn thing. All right, terminating video, and I'll get this up and get you some more. And it's all wrapping up for you. Hopefully you guys are following and I'm not losing you. I have more to explain, but I hope this gets it. 3A is going to be a nice little bonus also, but hopefully this is a bonus for you. Okay, today's video brought to you by George. Watch George turn around when I call his name. George. Hey, don't embarrass me. Georgie. That's right, good boy. Okay. So you guys can look up torsion, but this is how I would exhibit at the ends. The next couple of clips will show you how this exhibited in real life on the structure on each side, and the tape measure will even show per one side to the other that torsion as I talked about. This indicates also why the balance is no longer, this structure is no longer in equilibrium when we see this twisted at the base of 12 higher like that. So here, just narrating over. That's that twist you can find in the other videos I've made of this. This will show right by the two pieces of rebar standing up. Look at the floor of it, the top deck. It'll zoom in next right now. And it will show that crack is already present. This is right after the move, before detensioning. They had data. The next image will show that where the collapse happened between 9 and the structure, 910, and number 12, and at the canopy.